Okay, well, good morning, everyone. I have the pleasure to sort of put a few things on the table for your discussions, and I'm going to try to be provocative in making some statements, and by all means, shout me down and you know, talk it up. After yesterday's seminar, I went home and I thought, you know, there are a lot of things we can talk about, and as every speaker is going to bring up more and more things. So in self-defense, I thought maybe what I should do is just tell you in one slide, if that's all I have, is one slide of what my intentions are, and then spend whatever time I have, let's say 25 minutes or so, back into it. Okay, so this is my slide. Already. So I'm going to make a claim that there's a very well-known problem here, and that is the temperature dependence of viscosity. If you talk about glass transition, glass forming liquids, supercool liquids, dynamics, and what have you, eta of T. So eta is a viscosity, is a function of temperature. For supercool liquids, what we mean is really highly viscous liquids. Viscosity goes over 15 orders of magnitude. From room temperature down to some typical value like Tg. We can talk about what Tg is. Right? So this is very well known. There's no controversy about what the data is telling us. We have a set of data. I'm going to show you the data in a minute. And the question is, can we actually provide some theoretical understanding? And this is something that Jack and I and everybody else, I think, is very keenly aware of what the current situation is, more than I do, because I sort of backed into this problem a few years ago. I've been following MCT for a number of years. In the early days when MCT was used for dense liquids. By dense liquids, we mean liquids near the triple point. Even before that, there was this Boltzmann equation, renormalized kinetic theory, about how to modify the Boltzmann equation to get down to the critical point, critical fluids. Then we are ambitious, Bernie Alder, what have you, start talking about dense, more and more dense liquids, down to the triple point. And then Gitze, Lighthizer, Benzelius, Schulander, the MCT papers came out in 1984 now. So that's 26 years. All of a sudden, we were able to talk about glasses because structural arrest. Okay, so that's where it started. At least that's my background. But you know, I have not kept up with the community. There's a lot has been said. There's still some raging controversies, issues. So it's a very lively field, and we're really lucky to have the organizers to put together this program, bring us together. I hope that doesn't count against my 5 minutes, because that's just something I thought I should say, because it really is a wonderful opportunity. And let me take one more minute of my 5 minutes. There's a little plaque outside if you come from the parking structure. It was sort of dedicated by a fellow by the name of Robert Kirby. I don't know who Robert Kirby is. But anyway, Robert Kirby said the following: in racing as in life, slower is faster. I thought that was pretty interesting. Anyway, we're going to talk about slow dynamics here. Okay, maybe we'll go fast. I don't know. So, I claim that there's a problem that has not been fully solved, and that problem is how to calculate the viscosity of a supercool liquid using interatomic potentials and no other parameters. Right? So it's like a prediction. You don't adjust anything, just calculate. And we have the theories to do that, linear response theory, Green-Kubo, what have you. So we can go quite a ways, but unfortunately we cannot go all the way, because when you get down to very lower temperature, viscosity goes over many orders of magnitude, you run out of computing capabilities. So there is a well-known challenge there. So this, if I pose this as a problem, then I'm cheeky enough to come and tell you that last year we actually suggested a method where this might be done, at least partially done. It's for you, you're the judge. You tell me, yes, this is okay, no, this is not okay. So we can talk about this. All right. So I have a problem here, and I have a claim to be discussed. Then I have two implications, which we can discuss if we wanted to. If the time runs out, we can come back later on in the afternoon. One of the implications is that once you start talking about the viscosity, it's well known in the community. People talk about fragile liquids, strong liquids. So this concept of fragility is very much up in the air, and people still talk about it. They want to know what it is and how can you explain it and so on. Our claim, based on some things I'll put in front of you, is that actually fragile behavior is universal to all viscous liquids. Namely, if you have a liquid that you call strong or fragile, you would have something else that's the other part. So a strong liquid is silica. We claim silica actually shows fragile behavior at high enough temperature. Experiments don't show that because experiments don't go up to high enough temperature. But if you have a method to calculate this, you can predict that. And glycerol, for example, could also be one of these things that have a dual behavior. So strong and fragile behavior are actually two sides of the same coin. We think that's universal to all viscous liquids. This brings to the attention then there is a crossover, in fact two crossovers, from strong to fragile and then back to strong. And there are people who actually claim that they've seen more than one crossover behavior. So this opens up to some further interpretation, this discussion, which I hope people, I think people may want to jump in and talk about that. Then to connect with what Mike was talking to us yesterday about creep, I realized he's talking about creep from the perspective of statistical mechanics, statistical physics, talk about colloidal systems. I would like to make a statement about creep from the standpoint of, say, material science. That's just the structural deformation at very slow rates. And I'll give you some example. There are experiments there too. So this then becomes, if you buy, so here's the problem, here's a possible solution. If you buy this solution, then one of the implications that this may allow you to have a more unified perspective on relating transport phenomena and deformation phenomena. Again, together they make up rheology. So this may be a way to think about rheological phenomena from the energy landscape perspective, which we have heard about from various people. There are certainly people here working very much on that. And our contribution, which is actually the technique that actually made this approach feasible to calculate this, is what we call transition state pathway sampling. This is one of these rare event things. People like Chandler and others have done that. We happen to have stumbled upon a few years ago this method due to Parnello called metadynamics. And the key to metadynamics is to not really insist on following dynamics, but follow kinetics. That means energy activation. So activation energy is a big part of this, and that really comes very naturally out of the energy landscape. So that's my 5 minutes worth. And now, if the organizer stops me, I've already told you what I thought.
So before you go on,
yes, Dan.
When you say strength and fragility, these are two terms that have always puzzled me. They're a little vague, and people use them in a common sort of, or in lots of different ways. So from the perspective of your talk, what do you mean? Do you mean that strong is an Arrhenius liquid and fragile is non-Arrhenius?
Right.
So
That's it. Okay. It's as simple as that.
I just want to make sure, because in different ways, the different...
You'll come through in the next few slides, Dan. I think you see it very, very clearly. Well, this is what I claim is the problem, right? I mean, fortunately here we're not worrying about what experiments do. Experiments have been done. Here are the data. There's plenty of data of this kind. Austin Angel in '89 put up such a graph. Cleverly, he normalized the temperature in terms of what he calls TG, nothing more than that temperature where the viscosity is 10 to the 13 poise, or 10 to the 12 Pascal second. Okay. So everything is normalized to T over TG, And this is the log of the viscosity. So you go from an exponent of -4 to an exponent of 12, you got 16 orders of magnitude. Okay? So here's the silica data. I'd like to call your attention. Silica data is, well, at low temperature. To the right of the scale is low temperature. And the data shows essentially Arrhenius behavior because this is a log plot. All right, so take something else. Propanol, any one of these molecular propylene, they undergo this kind of behavior. So you might say, well, you know, this looks like an Arrhenius behavior. Then it goes into a regime where it's highly non-Arrhenius, super-Arrhenius. And if you think in terms of activation energy, that implies already just from the data that the activation energy here is essentially temperature independent. And then it runs into a regime where the activation barrier is highly temperature dependent. Now, some people think that there may be another transition further up, but we don't have to talk about that. So the data essentially suggests that you have liquids that behave like this, that has very, very severe, essentially some kind of a monotonic simple behavior, and this is also monotonic, but it's rapidly changing. And then you have something that doesn't seem to show much change at all. This region of high temperature is easy to study because we have Green-Kubo, we can do molecular dynamics, we can get low viscosity calculations, pretty high accuracy. Once the viscosity gets to be about 10 to the 3 poise or so, that's when the glass blower becomes interested, because then that's when the melt is stiff enough to sustain its own weight. Then you get into a regime where molecular dynamics runs out of gas, when we know why, because the stress correlation doesn't decay anymore. You cannot simulate long enough. In other words, the relaxation time is outrun your window of calculation. Not to follow nature, it's just because we don't have big enough computers. Even if we have big enough computers, that's not the way to go, because eventually you're never going to catch up. So at this point, you can understand why, those of us who do atomistic simulations, we don't really talk about this graph too much except for this end, because this is an embarrassing regime where we can't go any further. Now theory can, so maybe later on we can come back to anybody's theory, mole coupling theory, or what have you, and we can talk about that. So at the moment, I would say this is a challenge, right? So it's a challenge to those of us who like to do atomistic calculations. And the reason we want to do atomistic calculations is not because we can, but because we can actually uncover some mechanisms, how particles move when the system undergoes some sort of activation. You like to know, does it go like a chain-like thing, and does it go like bond switching? What do these particles really do? That gives you insight. Insight can then lead to further models. But we're stopped here. So up to this point, there's no, that I know of, there's no reasonable, credible curve that essentially spans this entire region. So that's the claim. Now I'm going to show you a result. It's already.
Can I ask you a question?
Yeah.
I mean, where is the audience in total? Dürr recently challenged this Vogel-Taman law in the paper, right? And he said it's all wrong because it doesn't fit very well. It's good approximation, but it's wrong in the detail. Is that something we all agree on, actually?
No, I have a big issue. I mean, he was making a big deal out of the fact that you extrapolate all of
Right.
it doesn't really diverge.
Right.
But if you constrain yourself to temperatures above TG, there's no issue.
Right.
And so we actually have a theory that actually predicts those curves over the whole range. At least there is
I like
a candidate for this. And it's the nature of the derivation that the theory does not, and we also derive, don't just perfect fit this focal relation from that model.
Okay.
But the theory applicability ends in TG. And so we think the extrapolation is still meaningful as an experimentalist, and from the model, extrapolate and determine that temperature. But you really do not expect, even from the model or in reality, to really have a divergence.
Right.
So I think just, you know, to put too much emphasis on the fact there is no point where the viscosity truly diverges in some special temperature isn't such a, maybe not surprising, and you know, maybe no, you know, so I don't see there's anything really wrong with local Fourier thinking on that basis. Does anyone else have a sort of thought on that?
What I would say at this point is that what I'm going to show you actually does not assume there's a TG, actually calculates TG, because it's a method to calculate viscosity.
But you're both talking about TG, which is not this one. This
Well,
TG is 10 to the 12 boys.
yeah.
No
There-
physics in it at all.
Right.
It's
Right.
just convenient.
Right. So,
So I
yeah.
think one must be careful about TG and TG.
right. I mean, there are other ways of defining TG.
Yeah, but he's just completely arbitrarily said
This is
10 to 12 boys.
right. This is a transport-based TG, and there are other people who look at TG from volumetric, specific heats and what have you. There are many ways you can define TG. So TG is not nothing, you know, that interesting actually. Anyway, so this is the problem. Let me just show you what.
One of the things worth noting is if you actually go beyond TG, the temperature dependence apparently changes. It's probably worth pointing out that.
Beyond which TG?
Well, you say where there's a maximum in your specific heat.
Well, yeah, but that's not that one. That's not 10
Well,
to 12
often
boys.
small molecules, it's not that far.
No, but it's not the same thing.
But in that vicinity, the main point is that there's a changing in character. I don't care which one of these TGs you choose, somewhat below TG, to where you get a more Arrhenius temperature dependence. So there seems to be a different temperature dependence in the last state.
Yeah, if I pick up what Jack is saying is that if you consider this mostly Arrhenius, then there's a transition from strong to fragile behavior. And then at some point, close enough to TG, whatever, there seems to be another transition back to strong. That's what he's saying, I think.
This is another reason.
Curves? Is that the red dot? Is that
The red dotted curve is the claim, yes. That red dotted curve is what we published this last year. Okay, I hope to get you interested, but I'm not going to tell you how we got this curve because that will take me more than the half hour. Plus, it's already published, and I can talk to anybody on the site. So my claim is that we now have a method that allows us to calculate this particular curve. This curve does not, by the way, take anything from the experiment. This curve is what we're able to calculate using the binary Leonard-Jones model of Cope and Anderson.
In the mechanical liquid, the similar curve also reported using
By whom?
Bush.
by Bush.
Yeah, actually, you even see hysteresis.
Yeah.
You see hysteresis
Interesting.
coming
I like to
down
see that.
like that and coming up again.
I like to see. Okay.
Bush is a Chinese group and also
Okay.
collaborated with some Danish scientists to find the thing along the normal mechanical.
Okay, if you can give me a ref, I'd love to know. So let me just caution you, for those of you who are sort of theoretically inclined, this is what we call a heuristic model. Heuristic model is not as good as what we now call a sort of a more rigorous model. So we have a better calculation than just this, okay? And that's actually a side remark. We claim that this already fulfills our initial wish of trying to put a curve that uses interatomic potential that goes essentially all the way through the entire behavior. So you can...
Is that red dotted curve supposed to be what you see in equilibrium in the liquid, or is that falling out of equilibrium?
Well, I have to, the red dotted curve is based on sampling this transition state pathway using this method. And then once you have the trajectory of this transition state pathway, then you have to do considerable statistical analysis to extract the activation barrier. And once you have the activation barrier as function temperature, then you get this curve. You don't have to make any statement about equilibrium, non-equilibrium. There's no, I mean, we can talk about that, but I can also tell you that what is needed to arrive at this red curve is inherent structure.
So you say this is from a binary Leonard-Jones
Binary Leonard, yes.
So what does that mean? When you say binary,
Right,
does that mean
because there are no, I mean, binary Leonard-Jones is not known to describe very well any of these liquids. So here you have a class of so-called fragile liquids. So this is a sort of a typical, prototypical fragile system. So, okay, you notice I'm not comparing the red dotted curve with the silica data. I'm only comparing with the selected.
Yeah, so let me ask the question differently. When I think binary, I think very simple. I think that there are two different species.
Big small
Two different
spheres.
species, now there are three potentials. that
Yes,
you
yes,
calculate.
yes, yes.
And so when you talk about a binary Leonard-Jones potential, that's a singular term. It sounds like there's only one.
Three potential. AA, AB, BB. Three potentials. And it's already worked out by Culp and Anderson, who started to simulate supercooled liquids using this binary
And
line.
then you also vary the relative magnitude of the three different potentials.
We just used their parameters. We didn't change anything. We didn't tweak anything. We just simply took. By the way, their model is pretty well benchmarked because they've calculated many things. They calculate diffusion coefficients. So it's over the years. I think the Culp-Anderson model came out in 1997 or so. Over the years, it's a very well-known model. People know that very well. We simply use that model, generate our own trajectories, and just calculate away. Yes, Jack?
Something kind of related to Mike's discussion yesterday. There have been some recent claims that there's in true amorphous solid formation, that you acquire a jump in the shear modulus of classes, somewhere below TG. And so then I guess that's something that should be examined more critically and true, and would be, of course, very significant. And so, I mean, there's only sort of this computation. You can only go so far in following the relaxation time increase, but then perhaps that, and that would be really just something to consider.
Yeah, I dare say that's something we can look into. Yeah, and it's not beyond what we can do. But at the moment, what we have done is very modest in terms of computational resources. We don't use the world's largest computer. We don't make huge systems. These are very modest systems. So I dare say that if there's additional features of interest, we could probably talk about that.
Yeah, maybe.
Yeah, sorry.
It's good if you tell us exactly how you calculate viscosity.
Oh yeah, already published. So I'll give you the paper.
And also why this
Yes, yes.
How do you arrive at this conclusion? Because otherwise, you're making a statement and we're not able to judge it.
Right. Okay. Well, so clearly, I know we can have A or B. We cannot have both. Okay. So my plan is actually hold you off on how to calculate. We do that over lunch or coffee and cookies. And then you sort of trust me for now. Let's just talk about the implications. Now, maybe you don't want to trust me, so I'll tell you.
I'll tell you why it's important that you say something about how you calculate it.
Yes.
This kind of behavior
Yes.
of viscosity or some properties that people measure.
Yes.
Are often seen because beyond the glass transition temperature,
Yes.
There is a change in behavior because the system falls out of equilibrium. A lot of things turn to Arrhenius. Okay, and this is not the fragile to strong crossover that people have discussed in other contexts, such as silica, where at least in computer simulations, that change is happening in a regime where one is able to equilibrate the liquid.
Yes.
Right. So, it's important to sort of, and the other thing is in computer simulations, in principle, you can have finite size effects, which could also give you a crossover like this, which is sort of not a very well explored area, but usually it doesn't come up because one is not able to do simulations at sufficiently low temperatures where it might become an issue. Right?
Yeah. Yeah.
So, but if you're saying now that you're going into temperatures where people haven't normally been able to calculate the viscosity, and you see this crossover, all of these questions are important to discuss.
Good. Good.
Yeah.
So I just ask for a little more patience. Okay? Because All right. So since Sri had just mentioned silica, this is so using the same technique here. You know, as Dan reminded us, this is for binary Lennard-Jones, and here's the data. This is what we could do without doing anything else. Now use a different potential. In fact, fairly low-grade silica potential. There are some better ones out there. Priya Vashishta has one that has 3-body interactions, but none of those. This is what we got for. Same thing, so the red curve now is our curve using this silica potential. And here are the Angel data. So here's the experiment, here's what we got. You notice Angel was motivated to call silica strong because the data didn't show anything that's non-Arrhenius. And while we do pretty well with our thing, we actually, from the calculation, predicted there should be a change. And this arrow is from Shortino. There was a Nature paper by Shortino who looked at the entropy calculation for silica simulation. They predicted there ought to be some sort of a crossover from strong to fragile at this temperature. We get it at higher temperature. And here's some MD result. These are heroic calculations by Horbach and Cope. Around the turn of the century, around 2000. And so while we believe this, these 2 points are our own MD simulation. Excuse me? Different potential. These two calculations use better potentials than ours.
Okay, look, if you take your potential,
Yes.
and you do MD with it,
Yes.
and then you do this other thing that you're not telling us about with it, do you get the same answer?
Yeah. We use our potential. Using MD, we get this answer. We use the same potential.
Those two don't know.
Yeah.
Yes. That's our.
But the MD data
But why
that
don't
showing that
you test your potential in the regime where Horbach and Cope tested? Because they did it about 10 years ago and should be, you know.
They use bigger computers. You notice we didn't get it as far because we cannot make those long. They use, that's why I call them heroic runs. They use very, very long runs.
This was 10 years ago.
10 years ago. I mean, be our guest. And these are not hard calculations now, right? So, but we were, we're actually, we were not all that interested. We think that this is somewhere in here. There should be a crossover from strong to fragile. Whether you believe Shortino, you believe our heuristic. At this point, that's not the main claim is that when we took our, here's the claim that I would like to like.
Can I ask you a question now? The Saika Voivod Shortino paper.
Yeah, right.
They did it at different densities, constant densities.
We just took their temperature. We put an arrow there.
Constant pressure. So these are going to be different. So it's a bit confusing to put all of that on the same.
Well, okay. So I mean, if you don't, there are so many details here that I really don't care. Okay. The thing that I care about is that let's not worry about this. Here's our prediction. Here's the data. I have not seen anybody give this kind of prediction before. If there is, I'm happy to quote it. Please tell me, all right? Never mind this. When Horbach and Cope did theirs, they said, they gone as far as they could. They basically ran out of gas. And they had this kind of data too. You can look at the paper. So basically just take away all these things and here's our prediction and here's the experiment. That's really what I want to say.
But still coming back to this discrepancy between him. I mean, if you go back one slide,
Yeah.
where you did the calculation for the Cope-Anderson mixture,
Right.
do you have a plot where you just, I mean, there also simulations have been done using MD and you have extracted.
Good question. Good. In fact, Thomas's question now leads me to the third slide.
Sorry, what was Thomas's question?
Comparing
We have switched from binary Lennard-Jones to silica. Now we're switching back. This is binary Lennard-Jones. Okay, and here are these. Here are the points of our calculation, and we compare with MD. Let me see. It should be on the next one. Is on the next one? If not, oh, I have to show that to you. But let me see. Where is that? You can find this. We checked that with. Oh, okay, I cannot find it at this point. Oh yeah, here it is. Okay. So this is the ND simulation, the usual green kubo, just like Horbach and Cope. And now for the binary Leonard-Jones case, and this is the red curve, the heuristic one. This is the better one. This is the one that I said I didn't even talk about. This is the extended green kubo. We've taken green kubo formalism, where you introduce inherent stresses and you look at correlations, you calculate stress correlation, the usual thing. And we then say, instead of using the molecular dynamics to calculate the stress autocorrelation function, you can postulate a network model where you calculate the stress relaxation using activated kinetics. All right. So again, the activated kinetics comes from our transition state pathway sampling. So use the same data. This is the green kubo calculation. This is the heuristic calculation. So this is the same input, same potential, but two different ways. We think this is a more refined way, and indeed we get different results. And the difference is in favor of MD in the region where MD exists.
For silica, the red curve you showed was the same method as the red curve here?
Yeah. This is the red curve for binary Leonard-Jones. All right. The red curve that I show for silica is using the same method but different potential.
No, but isn't this Leonard-Jones data showing you that that's not very reliable?
Yeah. So the heuristic the heuristic curve here is just a qualitative curve. We don't claim that this curve is all that reliable, right? But it does capture the overall physics, is all we're saying. Now for silica, we have not done the real. So this is the heuristic curve for silica, and we haven't finished. We haven't fully done the green kubo calculation. That's still. But we already can tell, the red curve overestimates. You see, since this is a log plot, there's actually significant consistent overestimate. We actually understand this, because this heuristic argument is meant to be an overestimate. It's like a upper bound estimation. So we actually have physical reasons for expecting that the data should lie on the right of this curve, and this is indeed what happened. So I think I've confused you enough, but let me now try to say one more thing. Kivelson, a few years ago, Kivelson and company, Angel's data, by the way, had something like 7 different liquids. Here, there's a set of data, 15 liquids, many more. So this is the Kivelson paper in PhysRev E around 1999 or so, 97 or so. They took all these liquids, they sort of massaged it a little bit and fitted it to an activation barrier as a function of temperature. So this is their way of plotting it. So we simply took their data. So all these symbols are data, except the two curves here of interest to us, because the heuristic model is this one. It's the dash curve. The green kubo model is the red one. All right. Notice that the heuristic curve indeed overestimates comparison to it does. It shows this plateau at high temperature, and then it has a steep rise. By the way, MCT for the binary Leonard-Jones, we know what that temperature is, 0.43 or so. That's right here. So it's right near the knee. So our calculation shows that there's no consistent overestimate, whereas the green kubo, the better calculation with the potential we can handle, is pretty much this curve. So at this point, I will use this as, sort of the most comprehensive test using all the data, and keeping in mind that the potential binary Leonard-Jones is not meant to fit any one of these. So all you can do is just look at the trend. There are scatters here. But basically, the lesson for us is that if you regard this as a temperature-dependent activation barrier, all the viscosity data is telling us is that at a high temperature, the activation barrier is low, and then at certain temperature, this is the critical part, what temperature? At certain temperature near TC, the activation energy starts to increase very sharply. That's all you can draw qualitatively from this. Now, whether you agree the accuracy is good enough or not, I think there are lots of things you can discuss. But this is basically our realization now. And it has come about because we're able to just calculate away. We don't make any assumptions that there should be such a temperature. We basically trust what the simulation gives us in terms of transition state pathways. And there's a lot of sampling, a lot of coarse graining there. It's not just one single process that controls this. So this is the end result of a lot of coarse graining averaging. That basically leaves you with the fact that, okay, at high temperature, all liquids, we now think, should have a very low activation. And then at some point, the activation energy is going to go up.
So when you say it has a low activation, what you really mean is that the thermal energy is sufficient to satisfy the activation. And then you reach a critical temperature below which the temperature is no longer sufficient to motivate that.
Okay, then.
So
Yes,
I think in the Stevenson-Tarjous way of plotting, there's no particular assumption about what the high temperature activation energy is.
Right.
Anything, they try to sort of have some interpretation of the values of the activation energy to find at high temperatures.
Yes.
Because whatever's on the y-axis is a fairly complicated beast. So
Right.
it's taking out absolute values of whatever you're plotting.
Yeah.
So I don't think there's any justification to say that the high temperature activation energy is low.
That's exactly what I'm saying. It's just that the thermal energy is sufficient to overcome it, whatever it may
It's
be.
higher at high temperatures.
Yeah. A relatively low
Jack, yes.
Okay, so you have all these great simulations, and there are all kinds of sort of path-based models for the high temperature activation energy. It sure would be nice to, and obviously it's relevant to all the systems. What can be said about the high temperature activation energy in terms of things you can measure and understand?
Okay. So let me go to the next slide. All right. So, we have two extremes now. We have a binary Leonard-Jones model, which...
Can I make a
yes.
comment about the previous slide? I mean...
No. Yeah.
So, I mean, that in principle, sort of two things that you could be saying in terms of the agreement with the curves that you calculate. So one is, so if you've calculated the viscosity directly from standard methods, right? Since the data collapse that's shown is what is expected for a wide range of materials, if you also calculate viscosities that fall on that curve, that's not particularly striking, right? It just means that you're doing things right.
Yes.
But presumably, if you're calculating that viscosity not from sort of a green Kubo type of approach, which is very painful and susceptible to large errors in computer simulation, then the fact that you're getting a reasonable agreement with the general trend that's expected is interesting. But like Thomas said, I mean, the best test for the method that you're using is not some comparison like this, but to compare with direct calculations and state points where it's feasible. That's how we...
Okay. I take that as your comment. I don't know. I don't disagree with that, right? But I guess I'm kind of anxious now to go to this next slide to show you what we got out of it. All right. I mean, we only use this to say that, okay, we try our best to use all the existing data, and this is our fit. So you be the judge as to what the interpretation is, right? So we don't say anything more about that until we go to the next slide now. Then we're going to say something new.
No, you're not trying, I thought you were calculating the viscosity for binary Leonard-Jones and silica.
No, sorry. Don't use the word silica. This is only for binary Leonard-Jones. No silica in here.
And everything that you're saying.
Right. So, all right. So now I come back. I say, we have also done calculation for silica. Let's plot the calculation for binary Leonard-Jones and silica on the same graph, rather than showing you a separate graph, and then see what message does that give us. I think now. That's why I think this next slide. I was so glad Dan was asking. The next slide goes back to the angel plot again. All right. So now we put everything that we have. So this red curve now is for silica. These blue points are for silica. The blue dotted curve is for binary Leonard-Jones. And these various symbols are for fragile liquids. All right. So we have strong data, strong liquid data, fragile liquid data. Now the only thing that's new beyond the angel plot is that we now have two curves here. So I just simply reminded you that for both of these, we have now a comparison. Yes, Jack?
I'm sorry, but something that really makes a big difference here is this constant volume or constant pressure you didn't mention. But that affects the apparent fragility appreciably. So just to know.
Yeah, the simulation was done at constant volume, and we're repeating it with constant pressure. And in fact, we're very interested in the pressure dependence of the activation pair, right? As you know, the people in silica.
Generally, fragility is largely affected by that condition.
Yeah, right. So that's something we need to look into. And yeah. So to go forward now, this is, by the way, you remember my very first slide. I said we have an implication that we claim that fragility is a universal behavior. This is the basis of our interpretation, okay? So this is the well-known plot, and everybody looks at this plot and thinks in terms of viscosity. If I were now to write a very simple transition state theory expression for viscosity, which is eta, let's say it goes like eta naught, e to the activation energy, let's call Q bar some sort of averaged coarse-grained activation energy over kT. There are plenty of people who use this kind of expression. Plenty, right? In fact, it goes back to Andrade back in 1932. There was a little note in Nature that actually said that. So basically now, if I'm interested in temperature dependence of viscosity, I can translate all this information into a temperature dependence of an effective activation barrier, an effective activation barrier. All right, since we have done the calculation of the viscosity here, so here's a plot of the effective activation barrier as a function of temperature for silica, a strong glass former, and binary Leonard-Jones, a fragile glass former. Right? No arbitrary parameter. So this is now activation barrier as a function of energy in units normalized to their own respective TGs. This is temperature. So you notice that at high temperature, silica and these glycerols and are very different in terms of the required. All right, this just came out of the calculation, so we didn't insist. But basically, what it's saying is that at high temperature, the fragile liquids have a much lower activation energy compared to the strong liquids, simply because the bonding is different. Chemical bonds are just stronger in silica than in binary Leonard-Jones. Nothing more. On the other hand, it also shows that this is not obvious, but it shows that by the time you get down to a low temperature behavior, they both approach the same way. At this point, a light bulb went on and said, okay, if you want a two-state model, here's a two-state model. Imagine you have an activation barrier as a function of temperature. It's a two-state model, all right? At high temperature, the activation barrier is low, and at low temperature, activation barrier is high. And fragility is nothing more than that intermediate region where you go from low to high. As you go from high temperature to low temperature, the activation energy goes from low to high. then the whole thing boils down to asking yourself, is it reasonable when I supercool liquid? All right, is it reasonable that if I supercool liquid from a high temperature, now we're talking about fictive temperature, right? From a high temperature to low temperature. If I'm deeply supercooling it, what do I expect? I expect the activation barrier to be higher. Where does that come from? It doesn't come from anywhere else from inherent structure. You already know from inherent structure, where you have done all the sampling and so on, you know that the inherent structure has a plot of the energy. These are now the energy of the basin, right? From high to low. This is temperature. This is energy of your basin. Inherent structure tells you this. In fact, Shastri, Stillinger, and you had that paper. It basically says that, you know, you have, by the way, this is a negative. So, okay, so this is low barrier. That is to say, if you do this steepest descent quench from a higher temperature, you fall into various basins. And those basins are not they're shallow. As you do your steepest descent quench, a lower energy, you can fall into some very, very low, but you know, nothing's infinitely low, so there is a low bend over here. This low bending over here is precisely that. So our final conclusion is that to reach this kind of discussion, you need thermodynamics, which comes from inherent structure, which has to do with the local minima of the basins. But that's not enough. You also need the saddle points because you need to hop over them. So I would now claim that to understand something as simple as the viscosity of swing temperature, a purely thermodynamic theory cannot do it all. You need kinetics. You need activation. Because you can have very, very low barriers, and you still need to hop out of them because you're never going to be stuck. If you have a perfect crystal that's very, very deep, then once you fall in, you don't get it out. But so long as you have a glass, it's metastable. Eventually, if you wait long enough, you can hop out. To get that kind of activation, you cannot do it with inherent structure. You need something that allows you to sample. Okay?
Just an observation, though. This temperature dependent is a basic assumption one of Adam Gibbs, and they certainly suggested in connection to thermodynamics that basically reciprocal Q relative to its high temperature value was reciprocal as the configurational entropy of the system, not vibrational.
Yeah.
And there's some merit for that connection, at least above TG.
Right.
There's a temperature range where there seems to be some applicability of that. So at least there's perhaps a chance that thermodynamics dictates temperature-dependent activation energy that you speak of.
Oh, yes. Incidentally, since you mentioned Adam Gibbs, we actually did a little more work. In this heuristic argument was essentially just the energy, the activation energy. So there was no entropy, configuration entropy. So we actually applied Adam Gibbs correction. And in fact, it did a better job in pulling this curve closer to where the green Kubo gave us. So we think that there is room for Adam Gibbs-like kind of statement, but at this point we're not saying anything too precise about that. But I think definitely configuration entropy could play a role.
Configuration entropy and test that idea, at least in certain regimes where you can be liberated.
Yeah, we have used the calculation method using density of states by Hoyer to calculate the configuration entropy. Okay, so if I can, this is it based on the interpretation of this. So now I'm ready to make this transition to creep.
Let's go back.
Yeah.
Just with that picture there.
Yeah.
So look, you've got the red curve and the blue dotted curve, and they both have this distinctly sigmoidal character, right?
Yeah.
And none of the data that is on there
is
that character.
Yeah.
Although if you go back to this Bush data or whatever, you might see it over there. But if you think this is a kind of universal feature, there's two things. Firstly, it's a bit surprising that no observed materials have got this second bend in the range of physics. You're saying In the silica glasses, it's too far over to the left for you to measure it. All the others, it's too far over to the right, but surely there must be materials in between where you would then see it. And then the other second point, which I'm not quite clear in view of this picture here, is that why doesn't it just go from one slope to another slope on that plot? Why does it have to come this S shape and come back, flatten out again on the right-hand side? I don't see it from there.
Let me see now. So, well, this fragility zone has a certain extent. So when that extent goes to 0, you just hop from low to high.
The Q here,
right.
QH and QL,
right,
on your viscosity plot,
right,
are slopes.
Yes, yes.
So you can cross from a low slope to a high slope without having to go at a higher slope still in between. And yet both your blue and your red curve, you have this region of very high slope.
Then you flatten out again.
Yes.
The schematics on the right is actually misleading because you would have a maximum in between. Well, the fragility zone can't be right.
To get the blue curve or the red curve there, where the maximum slope is between the two extremes, Q would actually have to go up.
Well, it's like an interpolation, right?
Because the curvature bending over twice, actually. As you said, it needs a different...
In both the red and the blue curves, the maximum slope is at neither extreme, it's in the middle.
Right.
So since the slope on that plot is Q,
It's not the slope.
Can't be the
this is the
slope.
log viscosity against TG over T.
That is true, but if it doesn't
TG is just a
translate to
parameter,
that-
so why doesn't that translate from this thing here? The log viscosity, A to T, if I take the log, I get Q over T. So the slope of a plot of log viscosity against 1 over T is Q.
But the slope to be taken as not as a derivative.
It is a derivative. Look at that picture there. Take it. Oh, no, I see. Okay. So it's the ratio. Yes, okay. So it would be quite useful to plot Q defined from that for the data.
Exactly.
For the experimental data.
Right. Oh, yeah.
No,
Okay.
the experimental data.
Right. So the experimental data are only in terms of eta.
Yeah, but you
not
can
in
just,
Q.
you can just
Exactly.
You can just take the
Well,
log of eta,
well,
multiply by T, and you've got Q.
Yeah.
But,
Right.
okay, so
Exactly. Yeah. That you can do.
okay, but I'm still not quite clear why your curves have to have this S shape rather than just having a low slope on the left and a high slope on the right. I don't quite see it.
Well, I guess we have to talk a little more, but offhand, I would say right now that there's plenty of data from experiments which tell us that you start out with at high temperature, you start out with a fairly Arrhenius behavior, and then you go into this bending up, okay, which is this one here. So there's plenty of data for that. There's some data now that's starting to suggest this happens.
Yeah,
For
so
example, in
that's
confined
But-
water.
Yeah. My point here is actually when you compare to the distribution of the temperature in the landscape versus temperature, okay, and that actually is a much broader temperature range than the transition at least in the metallic glasses, these people see, okay. So there it's around, what you see here in your blue curve, it is your 0.2, T of TG about the 0.2, you see transition, this blue curve in the activation energy.
Right.
That's a very narrow range.
It is very sharp, very sharp.
Very sharp.
Yeah.
Exactly. Transition.
Right, right.
It's random first order phase transition.
Yeah, yeah.
And over there, it's. So you must answer that point. It's a much broader temperature range, right? You have your distribution of the energy in landscape. Is it true?
No, I didn't understand the question. So you're referring to this graph here.
Yeah, it was a graph from blackboard.
Right.
Yes, on the lower right.
Right.
And isn't that a much broader temperature range than what he has here in the blue curve in the insert? This one, yes.
Well, this one, by the way,
It's very sharp. It's very sharp, and yours is very broad.
Yeah, it depends on what in fact I was. Yeah, what's your value of TG for that data? Because it is a broader range for for densities.
TG is pretty close to to the experiment. For silica, it came almost right on.
Binary linear.
But binary linear was within 100 degrees or so. I mean, sorry. So this curve here, the one that Conrad was just talking about, is exactly the curve that we have seen previously. Very sharp. This curve. That rise, it's really sharp. And the data shows very sharp
But
as well.
there's something else going on here as well. In this plot and in the plot that you just had,
Yeah.
all of the data are for polymers or molecular liquids, except for silica, which is different. Now, when we try to project this to metallic glasses are much more like the silica. They're still fragile, but they're stronger than a lot of these molecular liquids. So when we look at the curve 1 and 2 up there, and we're talking about the breadth of this,
Yeah.
metallic glasses are probably going to be somewhere in between.
Right. Okay. Yeah. Silica is very broad, right? As we have said. Where is the
But the magnitude of the potential levels.
Can I?
Yeah. Please.
Okay, the metallic glass in general, okay, this mixing things together totally is getting
It's confusing.
It's confusing. Okay, in the angel plot, we plot that over this T over Tg, okay? The metallic glass, if this is strong and this is fragile, the metallic glass are in between, depending on what kind of glass you take. If you take palladium-based ones, they are more fragile. These are the palladium, platinum, the new ones, all the multi-component systems. If you're taking the zirconium-based ones, they're over here, okay? So this is the slope, okay? And there are data up here, and there is a missing zone which we call of the viscosization business, and they have the high temperature ones, and they're over here, and it's the same over there. Now Bush, and also, I don't know this reference what you're saying, but Bush showed something in the vitriol one, which is this multi-component zirconium-based alloy from the Johnson group actually. They showed data which just looks like goes down like that, very narrow range, comes up again, and that's hysteresis. This is totally controversial, so okay? There are all kinds of arguments. This is a very narrow range. Where these data come down, there's a missing zone in between because the system likes to crystallize. This is a stable liquid far above the melting temperature of all crystals here, and he sees that.
And one part of that curve is ongoing, and the other part is unclear.
Yes, yes, you're right. It's hysteresis.
So this is in the stable liquid.
Looks like we're very much above that critical temperature or crossover temperature we discussed this morning already, which is the critical nose to crystallization, the mode coupling temperature, whatever we call it this way, or the emerging temperature. In my talk I will mention it. But this is a very narrow range of temperature, and nothing to do what you're seeing here in this distribution over there. I think this temperature range is
That's pretty high. That's very high. It's all above TC, isn't it?
It's all about so it's a.
It's very
I don't. You must answer that question. So that is the reason it's controversial is that nobody else had seen it in Iran, or one more group actually only. It's a multi-component system, and some say, okay, due to this parallel plate business and all that, this method, you might find some chemical phase separation in these alloys at that temperature. So you find that due to the rotating, because of the measurement technique actually, but maybe there is something going on. I don't know.
Well,
this is what I'd like to find out actually.
I mean, just.
That's only the basis of data.
So Austin has his recent thinking on the glass transition is that there's a liquid-liquid transition that's always involved.
Yeah, well.
And this, you know, I don't think it's generally true, but it's certainly plausible, especially in multi-component systems, that you will have a transition in the liquid state. Right?
Well, that's all we can.
But I'm not sure if it really sort of tells us anything too general.
No, but maybe one should, I mean, the vitrolite is a very interesting system maybe because even the diffusion, there's diffusion data covering 15, 16 orders of magnitude.
Right.
So maybe it would be worthwhile comparing with this. Because then
yes.
they really have, they start below TG and they end up far above melting temperature.
Comment there. There's very good data on borate losses over a huge temperature range. where the apparent activation energy looks very much like your number one there. So you might want to look at it. Borate, I mean,
Borate glasses, okay. Yeah, okay.
Mosquito and those guys at American University.
So where is the kingdom for borate?
It's near, as I recall, I don't remember all the details, but I recollect that it's thereabouts TG.
Well, but it's within the experimental range. They see the upper part.
They see it, they have it, because it's a
Oh,
very
that's-
robust class.
So Sid had borate in one of his earlier charts, and there was a huge amount of scatter.
It was huge. Yes, yes.
But
Right.
if you may want it to
Okay.
mosquito at all, I think it's pretty good data.
So it's possible somebody else has this group looked at the.
Oh.
See, there was a lady coming looking for you.
Well, it's possible, but it's also possibly not true. She may just come
She may have just been.
She may have.
When we did the string theory seminar, I noticed that this wasn't it.
So I better wrap up in any case. So in case you're interested in energy landscapes,
What did you learn from the energy landscape?
well, you know, now that we have the data, and so we start looking at this connectivity graphs, you know, a la Karplus and so on. So on the left is the binary Leonard-Jones, this connectivity graph. On the right is silica. They look quite different. And if you can try, by the way, this is not just a cartoon. We actually have information that allows us to make this. And if you then turn this into a plot, so this is now our current version, what we call a rough energy landscape, which is you would expect. This is the binary Leonard-Jones. That's what we mean by rough. You know, lots of oscillations. And what we mean by smooth here is fairly uniform. This is so these again came out of our calculation.
So it's,
How do you produce them?
Ah, okay. I have to again. I have to talk to you. Yeah, there's some.
Is there any geometrical or can you infer anything about the high temperature activation energy from the geometry of these generated?
Yeah.
I mean,
Yes.
never mind glasses. We don't have any theory of the high temperature transport.
The previous one has some.
I mean, there's Moe coupling theory that presumably a regime that the system is homogeneous. Does it have anything to say about the high temperature activation energy? I mean, it's valid anywhere. That's where it should be valid.
You should ask. Yeah, ask the Moe coupling.
no, that's what is changing actually during that narrow transition is you go back to your slide. What's the physical origin on that? In the blue one, for example.
Okay.
You think what's going on?
Okay. You mean here?
No, the insert.
This one.
Yes.
Okay. All right.
Where they connect.
All right. What's going on is that as you lower the temperature, okay, the system is able to find deeper and deeper wells.
Systematics, that trees.
That's why the activation energy goes up. Yeah. So as you lower basically, if you do your steepest descent quench, talk about fictive temperature. If you start out with fairly high temperature, you'll find some low-lying things. All right. But if you go to lower and lower temperatures, and if you do enough statistics, then you will find some deeper and deeper wells. But the deeper and deeper wells do not go forever. I mean, at some point, they run out of the basins. The basins have only finite depth. Nothing's infinite. So I would not, any theory, any model that says viscosity is diverging, no, it's just increasing rapidly, but it's not diverging.
So in this, we've been looking at polystyrene films that are, say, less than 90 nanometers, and they're down to, say, 10 nanometers, even less. And we in the gloss regime, we have a way of looking at relaxation there. You talk about how that's done. And it's related to a question that you mentioned about finite size effects. We find, and we'd like to understand, that we do see apparent Arrhenius behavior as a robust thing in the relaxation there. And that that plateau value is tunable with film thickness. It's very sensitive to the film thickness. Other people have recently seen this by very independent methods. So we're scratching our heads. What's that plateau? I should mention in the thin films we're not seeing any appreciable aging as opposed to bulk samples. So it's a little different. And so it's sort of kind of curious. So it would really be nice to have simulations and do a finite size study to see if anything like that is apparent in the simulations. And it really would be nice to understand what that plateau might mean. From it's actually a very practical thing because there are a lot of glossy polymer films that people make, and this is probably relevant to relaxation in those materials.
So I missed the start of that. Which plateau are you talking about?
The low temperature plateau. The measurements. The way the measurements are done. I just tell
This
you.
one, huh?
You put the polystyrene films on a rubbery. You pull on them. There's a buckling instability, and we watch the regression of the patterns. It's a very nice method. You can very clean. What the guys in Canada did is they put gold particles on the surface of the film. They heated it up. They sank them in, dissolved them by mercury, and watched them fill in. Much messier business. But surprisingly, we get the same results. So it seems, despite the very different nature of the measurements. And it seems to be, they're the weird thing. It's as you make the film sort of down to very small, where you still have good integrity films, the top plateau value actually goes down to the high temperature plateau. The gap goes, they go level. As if you associate the plateau with collective motion in an Adam Gibbs frame, it's as if all collective motion had somehow disappeared. It's curious. Anyway, the plateaus come together for some reason. This is a phenomenological thing.
So if you have data on this to show, don't that would be nice.
So that would be done for internet distribution. It's out for submission. So I'm sure my colleagues wouldn't be really wild about that. But I'd be happy to show people in person. Yeah. So that's.
So, how much time should we take? Are we out of time, or we? Oh, well, okay. So, maybe just a couple more slides then. The idea here is basically to notice that. We've been talking about the viscosity, but actually, was mentioned yesterday. The viscosity is nothing more than shear modulus times relaxation time. So we do 15 orders of magnitude in viscosity. Modulus changes maybe an order of magnitude, 2 orders at the most. So all the relaxation time. So basically, what we're talking about is a slow relaxation time problem. Now we can sample it, and then the question: then why don't we just exploit this isomorphism between thermally activated systems, thermally activated processes like what we've been talking about, viscosity, right? Green-Kubo's thermal activation. But now think about shear relaxation. Now there's this isomorphic relation between thermally activated systems and stress activated systems. So now instead of the state variable being temperature, I transform my problem to a state variable as the stress, and now I can talk about response, relaxation, what have you, to structure deformation. Okay, so that means now, since we already beginning to have a handle on how the activation barrier varies as a function of temperature, we can now ask how does activation barrier vary as a function of stress. So this opens the door to thinking about how systems deform and relax as a function of stress. Driven system. Driven not by temperature but by stress. So, we started to think about if you, this is a problem in, I guess, in material science, because, creep phenomena. There are all these mechanisms of creep. You have a Nabarro-Herring creep, you have Doring creep. Various people have thought about creep. Creep is nothing more than just the structural relaxation a very long time. Usually it's thought to be involving mass transport. Particles actually move from one side of the grain to another side, so the grains elongate, eventually the system elongates, and so on. So we can actually do this, and the experimental counterpart is, people who for years do internal friction measurements. And what they do is they look at a crystalline sample. They can either put a stress on it or put a strain on it. Let's imagine you stretch your system a percent or so, and you just wait and wait, and the system at some point starts to respond irreversibly. So this is called plasticity now because it undergoes plastic deformation. depends on what's inside your system, you have different modes of plastic deformation. So we started to think about, oh, now we can make some very, very clean, pristine samples because we can now do a nanocrystalline material. This is iron. So we have little small grains of iron, crystalline grains, embedded in some sort of a iron matrix, which is the grain boundary. So now we have grains inside a simulation cell, and the surrounding material, this is the matrix, now is some kind of grain boundary. The difference between grain and grain boundary is that the grains are highly ordered, it's crystalline. The grain boundary are misfits and so on. They're somewhat disordered. And as you strain the system, the question is that which part of the system is going to respond and dominate the response. It depends on whether the grains are stronger than the grain boundary or vice versa. Typically, the boundaries are weaker than the grains. The grains are stronger. Okay, so then it's no surprise then you start seeing atomic motion in response to your strain happening in the regions localized around the grain boundary. You can actually track this and figure out. The interesting thing is that from the standpoint of simulation, you can now look at stress relaxation over very, very long times. The reason it's very, very slow is because the system is very perfect. If you do an experiment, if you introduce imperfections, either depending on how you synthesize the system, you know, for example, these thin films are always vapor depositions or what have you. They have a lot of defects. The defects will actually allow the system to respond quicker. So this ideal simulation shows that you have something like this, and this is the mechanism that I can come back. So basically, you have this classic relaxation behavior of inelastic relaxation. So we're plotting the stress in the system as a function of real time in units of seconds. This is log time, okay? So what you see is that the system takes a very long time before it starts to relax, and then it undergoes a relaxation from some initial stress to some final stress. All right? So we even try to fit this not to a single exponential to a stretch exponential, and guess what is the beta? 0.7. No big surprise. So it's almost like an alpha relaxation. Okay? So nonetheless, what you see here is a relaxation in the system which occurs on the order of 10 to the 8th, 10 to the 9th seconds. That's over a year. Experimentally, they measure, using mechanical spectroscopy, they measure relaxation time of the order of 1,000, 10,000 seconds. Way, way off. And we understand that. That's because our simulation cells are too pristine. As soon as we introduce some additional defects, like some vacancies into our system, for example, this was the pristine case, high stress, very, very long relaxation time, you know, all to 10 to the 8th. As soon as we introduce some vacancies, the relaxation time drops by 3 orders of magnitude. So now the simulation is almost very close to the experiment. So this gives us now a control on this gives an understanding of what controls the relaxation time that you measure. Okay, so in some sense, this is another way of understanding relaxation phenomenon. Previously we were talking about viscosity, but now we're talking about creep. But essentially the underlying cause of deformation or response is the same, namely activation. Okay, so I want to leave that and then just finish up by saying, well, you know, there are many other problems which also offer challenges in terms of trying to understand long time scale behavior. When you confront with experiments, you need to make sure the experiments and the simulation are really trying to do the same thing. They have the same microstructure. And here is a short list of the examples we're thinking about. Since I'm a nuclear engineer, I'm interested in radiation damage, and we're also interested in corrosion phenomena. Corrosion phenomena is well known to have these kind of slow crack growth kind of thing. In stress corrosion cracking, you have 3 stages. You have corrosion, then you have a plateau, and then you have another rise. And so here's our plateau and a rise in viscosity. We've already talked about that. in creep. For example, this is the creep curve, thermal creep in steel. What people find is that these are experimental. They measure creep rate. And the creep rate can also goes from 10 to the minus something 13 to 10 to the minus 3. So again, 10 orders of magnitude. In this case, the state variable is the stress. All right, so you see that there's a plateau, there's a sort of a gradual increase, and all of a sudden the onset. So if you like, this will be our high temperature viscosity, exactly this. As you lower the temperature, at some point the viscosity shoots up. And here, at some point, the strain rate starts to shoot up. We think it's the same sort of general underlying behavior, activation, barriers, and what have you. This would be a little different. These two are actually a little different. You can have a dynamical crossover from fast, from strong to fragile. But if this crossover becomes an extended crossover due to some additional degrees of freedom, like transport, then this crossover then would give you a plateau. This is a very far out idea, all right? So not only do we have dynamical crossover, but we now are introducing the concept of extended crossover because you have additional mechanisms that can participate. And the mechanism in this case is that these corrosive agents, that not only do they make the cracks weaker at the crack tip, once you exhaust them, you need more supply. They have to come from farther away, and that's transport control. So this incubation time now requires transport in addition to reaction, okay? The ultimate thing is that this is the curve for cement. In cement, everybody knows this curve, but nobody can really explain it, and that is why if you mix cement powder with water, you got a slurry, you just sit there, as a function of time, the shear modulus goes from 0, basically, no shear modulus, up to some sort of coagulation period and then plateau, and then sits there, come back the next day, it rises too. You go from liquid to a stone. And this change is, all right, this is the sort of thing that seems to be very generic, and we think maybe there is a chance to think about them. This is really far out. So at that point, I think I thank you for your indulgence.